Hello again, and welcome back for another video here. So I do have to apologize right off the top that this was the only PDF that I failed to print out yesterday. So I'm going to be taking notes on a sheet of notebook paper, and hopefully we can get through all this stuff today. The good news is today's lesson is actually pretty easy. It's all review from Trig Pre-Calc, so it's all stuff that you've seen before. I'm going to be referencing the flip chart, which I have up on my computer. If I need to, I will pick up the camera that I have here, and I will point it at my computer. I think you can actually read stuff off the computer. So right off the top, we have the do now. You can look at that on the PDF. Assignment from yesterday. I actually have the PDF of that uploaded to my website for you guys. And now we're on to the first page where we have section 10.2, vectors in the plane. In case I didn't say it already, you are going to be able to do all of today's lesson without doing one bit of calculus. It is, again, entirely review from last year. So just as a reminder, if you have a quantity that has magnitude but no direction, that's called a scalar. So you're talking about speed, weight, mass. Speed, mass, quantities such as force, displacement, or velocity that have direction as well as magnitude are represented by directed line segments, and those are called vectors. So on that first page, you can actually see I have a point A, B. If I connect a directed line segment to that very same point, AB, all of a sudden this becomes vector V. And just to remind you guys from last year, when you're talking about vectors, if you're handwriting it, you do have to put that little half arrow symbol above it. If you are typing a vector, you can bold the letter, but since we're handwriting, we're going to use the half arrow there. And that vector, instead of using parentheses to describe it, you just describe its characteristics the same way that you describe the point. You just use angular brackets here. So this vector now has two components to it. It has a horizontal and a vertical component. Horizontal component being A, vertical component being B. And you can pick up that vector, you can move it anywhere in the plane, and it's still going to be the same vector. Some things to point out here, you have what is called the initial point of the vector, and you have what is called the terminal point of the vector. Those to me are not very difficult to master. Initial just means where you start, terminal is where you end. And one other thing, magnitude of a vector. If you're writing out magnitude, when I handwrite it, for some reason, I use a double magnitude bar. You can use the single magnitude bar as well. But magnitude just means size. And the size of the vector is just the length of the vector. Once you draw in your horizontal component and your vertical component, you can actually see you have a right triangle right there. And that right triangle, the hypotenuse is the magnitude. So there's just a quick formula for magnitude of a vector. Let's see, some stuff on that next page. A two-dimensional vector V is an ordered pair of real numbers denoted in component form. Again, this is called component form as AB with the angular brackets on it. The numbers A and B are the components of the vector V, so horizontal and vertical component. The standard representation is from the origin to that terminal point there. Magnitude denoted with the double bars right there is the length of the arrow, and the direction of V is the direction in which the arrow is pointing. So, the vector 0, 0, 0 is called the zero vector and has zero length and no direction. That was just from the second page of that. Next page we have magnitude of a vector. I don't know, should we just throw out a random vector here? Yeah, sure, why not? Let's talk about the vector 7, 2. In order to calculate the magnitude of the vector, what I always do, I mean, you have the formula that you can just memorize here, but whenever I do this, I always like to just sketch the vector. So 7, 2, right there. Now I can draw in the horizontal component and the vertical component. Let's just call this vector u. And to find the magnitude of vector u, again, once I draw it, I see the right triangle, and I can just say square root of 7 squared plus 2 squared. Key here is if you have any negativity, make sure you put the negative in parentheses. But again, this is just basic stuff that you guys know. 49 plus 4, square root of 53. So the magnitude of that vector is square root of 53. So again, that was from that page that just says magnitude of a vector. Now we have direction angle of a vector. The direction angle of a non-zero vector v is the smallest non-negative angle theta, formed with the positive x-axis and the initial ray and the standard representation of v as the terminal ray. So what that means is direction angle is just calculated from the same way that we read the unit circle. So the smallest non-negative angle going in the counterclockwise fashion, theta is right here. So to find theta, our direction angle in this case, let's see, I've got my opposite, I've got my adjacent. It looks like I can just do arctangent of opposite being 2 over 7. And then here, I guess since we're talking about a direction angle, you might be able to see this. My calculator is in degree mode. I don't know if you guys can see that. I can barely see it on my little monitor right here. But I find arctangent of, what was it, 2/7. The direction angle of this vector is approximately 15.945. And I'm going to say the word degrees. All right. Key things to look at here is you might have, like, this is a formula that you can use to find the direction angle, but we have to have those 4 different cases for the 4 different quadrants. But we're not going to get too into the weeds as far as direction angle is concerned this year. Next page that we have, again, this is after we see direction angle of a vector. You might have to do something called the head minus tail rule. The head minus tail rule is to determine a vector, or to find a vector in component form. And if an arrow has an initial point at x1, y1 and terminal point x2, y2, it represents the vector x2 minus x1, y2 minus y1. Really what we're looking at here is it's literally head minus tail. Head is your terminal point, initial point is your tail on this. So let's just say I have a vector that starts at 3, 6. Ends at 7, 4. All right. In order to find the component form of this vector, all we're going to do is the head minus the tail. The head is where the vector ends. The tail is where it starts. So I'd have 7 minus 3, comma 4 minus 6. And looking at that in component form, this vector is going to be 4, negative 2. And just to show you what that would look like, I've got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. This vector started at 3, comma 6 and ended at 7, comma 4. That's the vector v right there. And again, just like I told you guys before, you can draw this vector anywhere on the plane. It's still going to represent the same vector. 1, 2, 3, 4. 1, 2, So whether I draw vector v up here or vector v in standard position, it's still the same vector. Yow! Alright, so find the direction angle theta of the vectors v equals square root of 3, 1, and u square root of 3, negative 1. So again, I've got vector v is equal to root 3, 1, and u is equal to root 3, negative 1. This problem is just asking us to find the magnitude of each vector, and the direction angle of each vector. Again, just like I said up here, what helps for me on this type of problem is to draw the vector, and the vector doesn't have to be overly accurate here. I mean, root 3, 1, it's in the first quadrant right here. So I've got root 3 is my horizontal component, and my vertical component is 1. Only difference on vector u here is positive, negative. It looks like it's going to be in the fourth quadrant. So I've got root 3, comma, negative 1. Magnitude is going to be the same on these, I believe. Square root of 3 squared plus 1 squared. Again, just using the right triangle aspect of this. 3 plus 1, 4, 2. Looking over here, just like I told you before, you have to make sure to put your negativity in parentheses, or else, you fail. That's going to be 2 as well. To find my direction angle over here, that's theta right there. Theta, it looks like I can still do that old trick of arctangent of opposite over adjacent. Beep, bop, boop. Arctangent of 1 over square root of 3. I figured it was going to be something simple. 30 degrees. When I look over here, I can actually see I have the same right triangle right here. I can now introduce that concept of theta prime. Theta prime, in this case, is going to be equal to 30 degrees from the same calculation as over here. But what I want to find is theta. So to find theta, I mean, it's just problem solving at this point. I'm going to do 360 degrees minus 30 degrees, which gives me 330 degrees. And there you have vector direction and magnitude for 2 different vectors. Examples for you. Ooh, next one we have is we want to find component form of a vector with a magnitude of 4 and a direction angle of 60 degrees. So, magnitude of this vector is equal to 4, and theta is equal to 60 degrees. What's going to help you out on this one is to just draw a picture. 60 degrees looks like it's going to put it in the first quadrant. Magnitude is going to be 4. Theta right here is 60 degrees. Oh, look at that. I have a right triangle where I know the hypotenuse. I want to find the y-coordinate and the x-coordinate. So, the horizontal component and the vertical component. We're just going to call them x and y for ease of use here. To find the horizontal component, well, I can see I'm trying to find my adjacent, and I have my hypotenuse. So, let's see. So, toa. It looks like in order to find the adjacent side, I can just say cosine of 60 degrees is equal to my adjacent being my x over my hypotenuse being 4, which means my x is just going to be 4 cosine of 60 degrees. To find my y, I've got my opposite, or I want to find my opposite, and I have my hypotenuse. Opposite and hypotenuse, ooh, it looks like I can just do sine of 60 degrees is equal to y over 4, which means y is going to equal 4 sine of 60 degrees. And just real quick, I mean, I know on the unit circle, 60 degrees is right up here, so that point would be 1/2 root 3 over 2. Would have been much easier if I had just had that unit circle from my room here. 4 times 1/2, 2. 4 times root 3 over 2, 2 root 3. So it looks like in component form, this vector is going to be equal to 2, 2 root 3. And just to show you, I could have done the same thing on my calculator. 4 cosine of 60, 2, 4 sine of 60, 2 root 3. Now what's really actually pretty nice here is you can just set this up in the generic case. Let's say you know the magnitude of the vector and you know your angle. You're always going to have this setup right up here. So a nice little formula for you guys to memorize. The x component, the horizontal component of a vector, is going to be the magnitude of the vector times cosine of the direction angle. Your vertical component is always going to be the magnitude of the vector times sine of theta. Just a nice, easy pair of formulas. You guys had to memorize last year, but you can rememorize them. Vector addition and scalar multiplication. It's all stuff that you guys have seen before. For the first time during this video, I'm going to go over to my computer. So we're over here. Vector addition and scalar multiplication. If you want to pause, you can pause it and write that down. Basically, it's just saying if you add two vectors together, you have to I thought I stopped the video there for a second. To add two vectors together, you add the horizontal components, you add the vertical components, and then you have the sum vector. To multiply a vector by a scalar, you multiply each component by that scalar, and the opposite of a vector is just the opposite of each component. Just to drive this home, let's say I have vector u is equal to -1, 2, and vector v is equal to 4, 8. Finding these things right here, 2u plus 3v. That just means 2 times vector u plus 3 times vector v. I mean, really, you're going to see on the homework assignment that I post tomorrow, I don't even do all of these steps. I kind of do it in my head. -2, 4, multiply by 2, plus 12, 24. It looks like 2u plus 3v is equal to 10, 28. Simple math there, I think. Vector b, or sorry, part b is u minus v, which is equal to -1, 2 minus 4, 8. What I always tell people that helps out here, again, I do this part in my head, but instead of subtraction, think of it as opposite addition. So you take the opposite of this vector, and now you can add it together really easily. -1 and -4 gives you a -5, comma, -6. And last but not least, the magnitude of half of v. You got two ways to do this. You can take half of v and find the magnitude, or another thing that's really fun to do is just move that scalar outside of the magnitude. So it would be half times the magnitude of v, which here it would be half times the square root of 4 squared plus 8 squared. 16 and 64 gives me 80. So this would be half of the square root of 80. Now I have to simplify that. 80 breaks apart into 40 and 2 2 and 20, 2 and 10, 2 and 5, pair, pair. So this becomes half. We got 2 pairs of 2s, so 2 times 2 root 5, which ends up being just 2 root 5. You could have gotten the same thing by taking the magnitude of half of v, which would be half of v is half of 4/8, which becomes the magnitude of 2, 4, which ends up being the square root of 4 squared, 2 squared, plus 4 squared, which is the square root of 4 plus 16, ends up being the square root of 20. I know that 20 has a factor of 4, so that quickly becomes 2 root 5, whichever way is easier for you. I don't care which way you do it. They mean the same thing. Properties of vector operations, I'll put that up here for you.